Hello guys, as promised last time, and thank you for watching this video. We are going to cover backpropagation. So backpropagation is one of the things I spent a lot of time understanding. As you can see here, there's a lot of formulas and you need to understand why we are actually propagating backwards, why we are moving backwards through the network. What we have done to now is called feeding forward. So we move from the hidden layer to the next hidden layer and to the output layer, if that was the architecture. But now we are actually taking the error at the end. And let's say you are throwing a basketball to a hoop, and what we are doing now, we are checking how far from the hoop you are each time you throw the basketball, and giving you feedback on what to fix. Fix your let's say fix your posture, fix your arm, and your do I say your curve, until we get to know until we get to the desired output, which is hitting the hoop. So we are working backwards based on the error. So think of it like that. And then, if you don't understand the chain rule, I would recommend that you go and read about the chain rule and try some examples and do this for yourself, for your own understanding. So let's look at the first neural network we created in this video series. So we had the three neurons and three neuron hidden layer and an output. So what we did here, let's actually draw it up. We had the hidden layer with three neurons. I will just draw one neuron now. And this is the output layer. So, and then we had the ReLU activation function between here. And we had the set, which is weight x plus b, and then we have the activation function, which is a function of z, which is again max 0 set, and then we get the desired output. And for the not the desired output, sorry, we get the predicted output. And now we have a cost function, which is the, let's for example take the desired output minus, no, the predicted output, which is the y hat, minus the desired output, power of 2. And this is just getting the error. So if you think about it, we are in this layer and we have this error. And what we want to do now is find out how much, let's draw it quickly in an easy way for you to understand. So how much do we actually, we have the weights in the layer, let's call this layer L minus 1, and then this layer L, we have the weights in the layer L, and this will be directly, so this weight here will directly be connected to the output. And then we have the activation, which is for L minus 1, L minus 1. Let me do it on top, it's easier here. L for this, and then L minus 1, which is the activation of this neuron. And then we have the bias of the layer we are in now. So we have the bias here, we have this weight here, and then we have the activation of this function before. So our goal is to find how much the weights, the activation in the layer before, and the bias actually affect the cost function, which is the function that measures the error. Just stop up and try to understand this. So we try to measure how this actually affect this and how much they affect it. So let's take the set in this layer and try to do something like this, how much this is affected. So how far, if we move the w or the weights, how much do we affect the set. And then we do the same for the activation function, which is also the same. And then we do the same for the cost function, and the cost function gives us the desired output. So what do we want to do now? We want to propagate backwards. And when we say propagate this, we actually want to move backwards and find the derivatives, the slopes of course, of this function. So we start with the cost function. We want to find the marginal change in the cost function when we change the w. So when we change the weights, how will this, in this layer, how will this affect the function? So back to the chain rule, this will give us, you see this d, which I'm writing like this, is del. This means derivative, partial derivative of z with respect to, and remember, sorry for my bad handwriting, but this is L in this layer, W in the same layer, and then we have multiplied by the partial derivative of the activation there, multiplied by Z in the same layer, and finally we have the cost function and A in the same layer. So what we are going to do now is actually calculate each of this. So let's give it the numbers they actually have, which we already have given them up here. And in this case, I will switch the y hat with an A, since it's the activation of the last output, the last neuron. And now what we will do is we will find the partial derivative of the partial derivative of the cost function with respect to the weights in this layer. So this is, as you know from here, the weight function, the cost function looks like, looks like this. So this is the cost function. Now I swap this with A, and what I get here is, what I get here is 2 and A in the same layer. So minus the predicted value. We do the same for the activation function and do it with the Z in the same layer, of course, which gives us why are we doing this? It's because we could have the sigmoid function, we could have binary cross entropy. This depends on the function that you choose, on the activation function that you choose. In our case, it was ReLU. Sorry, this just jumped to the other page. It was ReLU. So that is the derivative of the activation function. And now we are doing the last one, which is the derivative of z with respect to the weights in the same layer. What does this give us? This is quite interesting because this gives us the activation of L minus 1 in the layer before. So when we did our one neuron, you remember when we are feeding forward, Z is equals to weight multiplied by X plus the bias. But now, instead of X, we have, since we are doing it at the output layer, X will be presented as activation of layer minus 1. So the activation of the neuron in the layer before the output layer. And then you add the bias. That's why we get this. And putting it all together, we actually get d del C del W is equals to A, which is here, L minus 1 multiplied by the derivative of Z in the same layer and 2A in the last layer minus Y. So I know this is a lot of math, but take some minutes and think about this. What is this representing? And remember, we actually drew it up here. So when we are changing the weights here, it affects the set, it affects the activation function, and it also affects the cost function. So that's why we are doing this we're doing this chain rule derivative here, and we get the actual value as this. And then we do the same thing for the other values which were up there with respect to actually, now let's just take the bias, and the bias is going to be BL in the same layer. So we do the same, d set dl divided by, not divided, sorry, derivative of b in the same layer, and the rest remains the same actually, because it's just the first thing that we are changing. So when I say the first thing, I actually mean in this setup here, we just switched from the weights to the biases, and then we have to follow the same script here. So we do the same dz db, and then the same thing here. And the last but not least, we have dA, dz in the same layer, and the cost function, the output layer, and dA in the same layer. Everything from here remains the same. So we will have the activation function set in the same layer, derivative, and the last cost function remains the same. Activation in the last layer minus the expected value. And when we look at the bias, we look at z, which was z is equals to, let me remember again, the weight and a minus in l minus 1 plus the bias. This is a constant in this case since we are doing the derivative with respect to the bias, and this becomes 1. So we add the 1 here. This is important to remember. We have done for the weights and the biases now, and this is for a single, what do I say, for a single neuron, and we are moving backwards. So we have the cost with respect to the bias and with respect to the weights, and that's one part of it. So that's at least the first part, and now you can actually propagate backwards and go back into the there and then go back now, since you have the values of the derivatives of these two. And for now we cannot change the what do I say, the activation function yet, but we would need to do the derivative of the cost function with regards to the activation function, and in the layer before, of course. So this will be for another video, but for you to understand the math here, you have to stop up and think about how we actually influence the different. So you have the w, the weights, and then you have the layer before and the biases, and all of this influence the straight into the function, which is z, and then from there this influences the activation function of z, and this also influences actually the loss function, which is the cost function, and this gives us the desired value. So you do test for this and this, and this is something we can cover in another video. But now you know how to do the derivative, finding the derivative of the full cost, the cost function with regards to the weight and the bias. For this, I can quickly give you an overview of what it is. So quickly, let's find the derivative of the cost function with respect to the activation in the layer before. So this will be the cost function, no, the z in the layer you are in now, and derivative with respect to a, activation minus 1, the layer before, and now the rest remains the same, dA in the same layer, and dz in the same layer, and lastly the cost function, and with regards to the activation in the same layer. So this will give us, if you remember, the set was equals to this a l minus 1 plus b. This derivative of this will give us w in the same in the layer we are in. So this becomes actually d co d a l minus 1 gives us the weight in the layer we're in multiplied by the rest of the function that we already have done a couple of times now, the same layer, and 2a in the same layer minus y. So those are the formulas that you will be using for backpropagation, and you will need to do a sum over all the layers, of course, and this is just for one neuron to one output. You will need to sum over all the layers, and remember that this is just to show you how the math works. So After doing the math on backpropagation, let's take a quick look at simple simple example, and I will be going through the code with you and showing you different variations of the code that will give us different curves for the loss function. And let's quickly recap. So we did the derivations, and now we are going to do this for a simple neuron as the initial example, which we did already. We have the set, which is the weights transposed multiplied by x plus the bias, and then we have the activation function. In this case, it's a sigmoid. And then we have binary cross entropy in this context, which we will also we will implement in code. The chain rule, same chain rule here. This now we are just changing the y hat with the activation function, which also is another way of doing this. So after doing the math here, you can check this later. You just get a sigmoid gets derivative like this, and then you do the y hat the with the respect to z, and you get this, and you do the d set dw, you get this, and the set db, you get one, as we already did. So what's important to understand here is that these are the values for the loss function when deriving the loss function with respect to weight, you get this, and with respect to the bias, you get this. And when we are, this is just for a single training example, and now we will have a batch and n examples, and we typically do the average of the gradients, as you will see here. We divide by the batch, which is we will see down here in the code, and this is going to be the output here. And same thing for the bias, we will do the same, and we will get the average. So let's actually jump to the code. So what I've done here is I've just generated some linearly separable data, and I'm using the random seed 42 here because I want the output to be I want to be able to regenerate the output. I have the batch size, which is n 200. I have the dimensions, this is 2, and x and x positive and negative values, and then we stack them up and reshape to -1 1. So this is just getting the numbers in place. This is you don't need to use a lot of time on this. Just understand that we are just generating some linearly separable data, and the parameters now, these are important because the weights are in the shape of the dimension 2 and and 1, and we have the bias, which is biases that are initialized to 0, and we have the learning rate, which we haven't covered a lot yet, but this is the size of the steps that you will take in the gradient descent. So it means how, if I have 0.9, those are huge steps, so you will be moving each gradient step move, you will move 0.9, and here I will move 0.1, which is kind of used a lot, and you choose based on your the problem you're solving. The activation function is the sigmoid activation function. We have discussed this earlier. 1 divided by 1 plus the exponential of minus z. And and then we do the loss history. We are actually saving the loss function in each pass, each forward pass, and trying and plotting it later. So we define set here, x dot w. This is just a matrix multiplication, and then we add the bias. Y hat is the sigmoid set. This is the output layer. And then we do the binary cross entropy. And then we append the loss history to the list here, which is open, which is empty. So now is the backpropagation part. So d set, which is this here, we will calculate this first. So notice that we are actually calculating only this first, so that we get y hat minus y, and then we calculated the cost function's derivative with respect to w. So y hat minus y, and then we do the weights with respect to the weights, and this gives us actually x transposed, and my matrix multiplication with dz, which is actually the value here somewhere, x, and multiplied by the y hat minus y, which is represented here. And we divide by the batch size, as we already have defined the batch size here. That's cool. And now we will go and do the bias, which is dz y hat minus y, and we find the average of this, the mean of this. So, and good thing here is you can always, let's see, yeah, you do the mean. And then the gradient descent, we haven't covered this yet, but what the gradient descent does is it takes the position you're in now, and then it finds the steepest steepest slope of yeah, and this is the derivative, of course, and then it applies the learning rate. So you take the weight, and then the output of this will be the weight now minus the learning rate multiplied by dw, which is here, and we do the same for the bias. So this is for the weights and for the bias. And we will be printing, since the range here is we are actually doing a for loop that goes into 1000 up to 1000, and for each step we will divide by 100 and plot, not plot, but show you the loss of the step, and we will print the bias and the weights. So let's run this and you will see the values down here. So we initialize the bias as 0, and step 0 you have the loss and very small values for the bias, and the bias is still 0. And after 100 steps we have actually started updating the bias and the loss is going down. This is what we want, and we can study this and see that for each step the loss is going down, the loss is going slowly down, and the bias and the weights are changing, and the final loss is 0.032. As you can see here, this is how the loss looks in each step. And I can do something here which is interesting. Let's change the learning rate from 0.01 to 0.1 and see what happens to the curve. As you can see here, the curve was somewhere here. Now it actually falls down here, and you can see the loss has gone is lower than it was before, and the bias is a little bit more if I'm not if I remember correctly. But just try this out. Try to find out why we actually are getting this steep fall when we take a huge drop, when we take a huge learning rate compared to this small learning rate. Let me take 0.001 to just show you something, and let's see what happens. You see, this happens. So convergence takes time because you are taking very small steps in your learning rate. You're actually not taking the biggest steps. So you will be using a lot of time to converge to the final loss. So do this, test it out, and this will be available for you in this notebook, and try to understand how the learning rate is connected to the gradient descent and how we actually find the weights and biases. Thank you for this video. In the next video, we will look at convolutional neural networks and how they work with a filter and other properties. Thank you.